Hey there. How was your day? Wherever you are in the world, whatever time it is, I'm so glad you're here with me tonight. We're about to embark on a journey to one of the most mysterious and fascinating places in our solar system. A place where storms rage for centuries, where diamonds might rain from the sky, and where secrets lie hidden beneath layers of swirling clouds that stretch deeper than Earth's entire diameter. Tonight, we're diving into the alien world that lies beneath Jupiter's mesmerizing surface. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination drift through the cosmic winds of our solar system's giant. If you find comfort in these gentle explorations of space and science, I'd be grateful if you consider subscribing and liking this video. It helps the algorithm find more curious minds like yours, and it would mean the world to me as we explore the wonders of our universe together. I'd love to know where you're listening from tonight. Drop your time and location in the comments below. Are you watching Jupiter rise in your evening sky? Or perhaps you're on the other side of the world where dawn is breaking? There's something beautifully humbling about discussing Jupiter while we're all scattered across our small planet, looking up at the same cosmic dance that has fascinated humanity for millennia. Picture yourself standing on a spacecraft, floating just above Jupiter's cloud tops. Below you stretches an ocean of atmosphere so vast it could swallow Earth whole. The bands of cream and amber clouds swirl in hypnotic patterns, driven by winds that howl at speeds that would tear apart any hurricane on Earth. But what you're seeing is just the beginning of the story, because beneath these clouds lies a world so alien, so extreme, that it challenges everything we thought we knew about planetary formation and the limits of matter itself. Welcome to this journey through Jupiter's hidden depths, where we'll discover how pressure and temperature create states of matter that exist nowhere else in our solar system, where we'll explore the possibility of diamond rain, metallic hydrogen seas, and a core that might not be solid at all. This isn't just a story about a distant planet. It's a story about the fundamental forces that shape worlds and the incredible discoveries that await us in the depths of space. For centuries, Jupiter appeared to us as nothing more than a wandering star, moving slowly against the background of fixed constellations. Ancient astronomers called it the King of Planets, but they had no idea just how accurate that title would prove to be. When Galileo first turned his telescope toward Jupiter in 1610, he discovered 4 moons dancing around the giant planet. This simple observation shattered the Earth-centered view of the universe and opened our eyes to the reality that worlds could have their own smaller worlds orbiting them. But even Galileo couldn't have imagined what we've learned about Jupiter in recent decades. This isn't just a large planet, it's a failed star. A world that came tantalizingly close to igniting nuclear fusion in its core. If Jupiter had been just 50 to 100 times more massive, our solar system would have been a binary star system, with 2 suns illuminating the cosmic dance of planets. Instead, Jupiter became something equally remarkable. A gas giant so massive that it contains more than twice the mass of all other planets in our solar system combined. Its gravitational influence shapes the orbits of asteroids and comets, acting as both a shield that protects inner planets from impacts and a gravitational shepherd that maintains order in our cosmic neighborhood. The journey to understand what lies beneath Jupiter's clouds began in earnest when we started sending robotic explorers to visit this giant world. Pioneer 10 and 11 gave us our first close-up glimpses in the 1970s, followed by the more sophisticated Voyager missions that revealed Jupiter's complex system of moons and rings. But these early missions could only observe Jupiter from the outside, studying its cloud tops and magnetic field, while the secrets of its interior remained locked away beneath layers of increasingly dense atmosphere. Everything changed when the Galileo mission arrived at Jupiter in 1995. This ambitious spacecraft didn't just orbit the planet and study it from afar. It released a probe that actually descended through Jupiter's atmosphere, becoming humanity's first direct explorer of the giant planet's hidden realm. The probe's journey lasted just 58 minutes, but in that brief time, it revolutionized our understanding of what lies beneath those mesmerizing clouds. As the probe fell through Jupiter's atmosphere, it encountered conditions that pushed the boundaries of physics and engineering. The temperature climbed from the frigid cold of space to hundreds of degrees above the boiling point of water. The pressure increased from the near vacuum of space to crushing forces dozens of times greater than what we experience at Earth's surface. And still, the probe was only scratching the surface of Jupiter's atmospheric depths. The data transmitted back to Earth during those precious minutes painted a picture of a world unlike anything in our experience. The atmosphere wasn't just a thin shell surrounding a solid surface, as we find on rocky planets like Earth and Mars. Instead, it was a vast ocean of gas that grew denser and denser with depth, eventually becoming so compressed that the very distinction between gas and liquid began to blur. This is where our journey into Jupiter's interior truly begins. Because as we descend deeper beneath those swirling cloud tops, we encounter states of matter and physical conditions that exist nowhere else in our solar system. The story of what lies beneath Jupiter's clouds is really a story about transformation, about how the familiar elements that make up our world behave in ways that seem almost magical under extreme conditions. Imagine descending through Jupiter's atmosphere like an explorer diving into the deepest parts of Earth's oceans. But instead of water growing denser around you, it's hydrogen and helium, the two simplest and most abundant elements in the universe. At first, this descent feels familiar. The hydrogen exists as a normal gas, just like the hydrogen we know on Earth. The atoms bounce around freely, colliding with each other in the chaotic dance of a gas under pressure. But as we continue our descent, something remarkable begins to happen. The pressure around us grows to levels that dwarf anything we experience on Earth. The weight of thousands of kilometers of atmosphere above us compresses the hydrogen gas with forces that would crush any material we know. Under these extreme conditions, the hydrogen begins to behave in ways that challenge our everyday understanding of matter. First, the gas becomes so dense that it transitions into a liquid state. But this isn't like water condensing from steam. This is hydrogen being squeezed so tightly that the atoms can no longer maintain the loose, bouncing arrangement of a gas. They're forced into the more compact arrangement of a liquid, creating vast oceans of liquid hydrogen that stretch for thousands of kilometers in every direction. As we descend even deeper, the pressure continues to mount. We're now experiencing forces hundreds of thousands of times greater than Earth's atmospheric pressure. The liquid hydrogen around us is compressed to densities approaching that of water, despite being made of the lightest element in the universe. And still, we're only partway through our journey to Jupiter's core. At these incredible depths, approximately 20,000 kilometers below the cloud tops, something truly extraordinary occurs. The liquid hydrogen undergoes another transformation, one so alien that it wasn't even predicted by scientists until the middle of the 20th century. Under the crushing pressure, hydrogen atoms are squeezed so tightly together that their electrons are stripped away and begin to flow freely, like electricity flowing through a wire. This creates a substance called metallic hydrogen, a material so exotic that we've only recently been able to create tiny amounts of it in laboratory conditions on Earth. In Jupiter's interior, metallic hydrogen exists in quantities beyond imagination, forming an ocean that extends for thousands of kilometers in all directions. This isn't just a scientific curiosity. The metallic hydrogen ocean plays a crucial role in one of Jupiter's most distinctive features, its powerful magnetic field. Unlike Earth's magnetic field, which is generated by the motion of molten iron in our planet's core, Jupiter's magnetic field is created by the flow of electrical currents in this vast ocean of metallic hydrogen. As Jupiter rotates once every 10 hours, the metallic hydrogen swirls and churns, creating electrical currents that generate a magnetic field 10 times stronger than Earth's. This magnetic field extends far out into space, creating a magnetosphere so large that if we could see it from Earth, it would appear bigger than the full moon in our sky. But our journey is far from over. Even the metallic hydrogen ocean, vast as it is, represents only a portion of Jupiter's interior. As we continue our descent toward the very heart of the planet, we encounter mysteries that continue to challenge our understanding of planetary formation and the behavior of matter under extreme conditions. Recent discoveries from NASA's Juno mission, which has been orbiting Jupiter since 2016, have revealed that the planet's interior is far more complex and dynamic than we ever imagined. The spacecraft's precise measurements of Jupiter's gravitational field have shown us that the transition between different layers isn't as neat and orderly as we once thought. Instead, Jupiter's interior appears to be a swirling, mixing cauldron, where different states of matter interact in ways we're still trying to understand. The journey continues as we approach what scientists believe to be Jupiter's core, a region that may not be the solid, rocky ball. Instead, that early theories predicted Juno's data suggest that Jupiter's core might be partially dissolved, mixed with the surrounding metallic hydrogen in a way that creates a fuzzy boundary rather than a sharp transition. This discovery has forced scientists to rethink their models of how giant planets form and evolve over billions of years. But perhaps the most intriguing mystery lies in the possibility of diamond rain within Jupiter's depths. Under the extreme pressures and temperatures found in the planet's interior, carbon atoms, if present, could be compressed into diamond crystals. These diamonds would then fall like rain through the layers of liquid and metallic hydrogen, potentially accumulating in vast deposits at certain depths within the planet. The concept of diamond rain sounds like something from a science fiction novel, but the physics behind it are surprisingly straightforward. In Jupiter's atmosphere, traces of methane exist alongside the dominant hydrogen and helium. As we descend deeper into the planet, the crushing pressure and rising temperatures break apart these methane molecules, freeing carbon atoms that would otherwise remain locked in their gaseous compounds. Under the immense pressures found thousands of kilometers below Jupiter's cloud tops, these liberated carbon atoms don't simply float freely. Instead, they're squeezed with such tremendous force that they form the crystalline structure we know as diamond. Picture billions upon billions of these precious gems, each one formed not in the slow geological processes we see on Earth, but in the rapid, violent compression of Jupiter's interior. These diamonds wouldn't remain stationary. As they form, they would begin to fall through the layers of increasingly dense material below them. Imagine standing in a rain of diamonds, each one catching and reflecting light that filters down from the layers above. But this isn't a gentle shower. These diamonds would be accelerating through liquid hydrogen at tremendous speeds. Their fall only slowed by the increasing density of the material they encounter as they descend deeper into the planet. The size of these diamonds remains a mystery that captures the imagination. They could range from tiny crystalline particles, no bigger than dust motes, to massive gems the size of boulders or even larger. The extreme conditions within Jupiter's interior could potentially create diamond formations unlike anything we've ever seen on Earth, compressed and shaped by forces that our planet simply cannot produce. As these diamonds fall deeper into Jupiter's interior, they would eventually reach layers so dense that even diamond cannot penetrate further. Here, in the deepest reaches of the planet, vast accumulations of these precious stones might exist, creating diamond mountains or seas of crystalline carbon floating in oceans of metallic hydrogen. It's a treasure trove beyond the wildest dreams of any earthly prospector, locked away in conditions so extreme that no human technology could ever hope to reach it. But diamonds aren't the only exotic material that might form in Jupiter's depths. The same extreme conditions that create these carbon crystals could also forge other unusual compounds and elements. Scientists theorize that the interior of Jupiter might contain materials that exist nowhere else in our solar system, substances created by the unique combination of pressure, temperature, and chemical composition found only within this giant world. The temperature gradient within Jupiter tells its own fascinating story. Near the cloud tops, temperatures plunge to minus 145 degrees Celsius, cold enough to freeze nitrogen solid. But as we descend through the layers we've been exploring, the temperature climbs steadily, driven not just by the compression of material above, but by the heat generated from Jupiter's own formation billions of years ago. Deep within Jupiter's core, temperatures may reach 20,000 degrees Celsius, hotter than the surface of the Sun. This isn't the result of nuclear fusion like we see in stars. Instead, it's the leftover heat from when Jupiter first formed, compressed and trapped beneath thousands of kilometers of dense material. The planet is still slowly cooling from its violent birth, radiating more heat into space than it receives from the Sun. This internal heat source drives much of the dynamic activity we observe in Jupiter's atmosphere. The Great Red Spot, that massive storm larger than Earth itself, has been raging for centuries, powered by the convection of heat rising from the planet's interior. The colourful bands and zones that make Jupiter so visually striking are also driven by this internal heat engine, creating circulation patterns that transport energy from the deep interior up to the visible cloud tops. The Juno mission has revealed that these atmospheric patterns extend much deeper than we previously imagined. The spacecraft's microwave radiometer can peer through the cloud tops and map the movement of ammonia gas hundreds of kilometers below the visible surface. What it has found is a complex system of jet streams and circulation cells that extend deep into the planet, connecting the surface weather we observe to the exotic conditions in the interior we've been exploring. These deep atmospheric currents play a crucial role in mixing the different materials within Jupiter's interior. The boundaries between the various layers we've discussed aren't rigid barriers, but dynamic zones where materials can mix and exchange. The metallic hydrogen ocean doesn't sit in perfect isolation beneath the liquid hydrogen above it. Instead, convection currents and turbulent mixing create a gradual transition zone where the properties of matter change continuously with depth. This mixing has profound implications for our understanding of how Jupiter formed and evolved. The planet didn't simply accrete material in neat, orderly layers. Instead, the process was chaotic and dynamic, with different materials mixing and separating under the influence of gravity, pressure, and the planet's rotation. The Jupiter we observe today is the result of billions of years of this ongoing internal evolution. Recent computer simulations suggest that Jupiter's interior might be even more dynamic than we previously thought. The metallic hydrogen ocean could be in constant motion, driven by the planet's rapid rotation and the heat flowing upward from the core. This motion would create complex three-dimensional flow patterns, similar to the circulation we observe in Earth's oceans, but operating under conditions so extreme that the very nature of matter is transformed. The magnetic field generated by these currents in the metallic hydrogen ocean extends far beyond Jupiter itself, creating a magnetosphere that stretches millions of kilometers into space. This magnetic bubble captures charged particles from the solar wind and from Jupiter's volcanic moon, Io, creating radiation belts so intense that they would be lethal to unprotected humans within minutes. The interaction between Jupiter's magnetic field and these trapped particles creates some of the most spectacular auroras in our solar system, lighting up the planet's polar regions with curtains of glowing gas visible even in the depths of space. Understanding Jupiter's interior also helps us understand the formation of our entire solar system. As the largest planet, Jupiter played a crucial role in shaping the distribution of material during the early days of planetary formation. Its immense gravitational influence prevented the formation of a planet in what is now the asteroid belt, instead scattering rocky debris that continues to orbit between Mars and Jupiter today. The composition of Jupiter's interior also holds clues about the conditions present in the early solar nebula from which all the planets formed. By studying the ratios of different elements within Jupiter, scientists can piece together the story of how our solar system evolved from a disk of gas and dust around the young sun into the complex arrangement of worlds we see today. The exploration of Jupiter's interior represents one of the greatest challenges in planetary science. Unlike the rocky surfaces of Mars or the Moon, which we can study with landers and rovers, Jupiter's interior remains largely inaccessible to direct exploration. The crushing pressures and corrosive atmosphere would destroy any probe long before it could reach the truly exotic regions we've been discussing. Yet through a combination of spacecraft observations, laboratory experiments, and theoretical modeling, we continue to piece together the puzzle of what lies beneath those mesmerizing clouds. Each new discovery reveals just how alien and wonderful this giant world truly is, reminding us that our solar system contains realms of experience far beyond anything we encounter on our small, rocky home planet. As we float here in our imagination, suspended above Jupiter's cloud tops, we can appreciate the sheer scale and complexity of the world beneath us. Every swirl in the clouds below represents atmospheric movements connected to processes occurring thousands of kilometers deeper, in regions where matter behaves in ways that push the boundaries of physics and challenge our understanding of what's possible in the universe. The story of Jupiter's interior is still being written. With each orbit of the Juno spacecraft, with each new computer simulation, with each laboratory experiment that recreates the extreme conditions found within giant planets, we add new chapters to our understanding of this remarkable world. The diamonds falling through metallic hydrogen seas, the partially dissolved core mixing with the layers above it, the complex dance of magnetic fields and electrical currents, all combine to create a planetary interior unlike anything else we've discovered in our cosmic neighborhood. Tonight, as we continue our descent through Jupiter's alien depths, we encounter phenomena that stretch our understanding of physics to its absolute limits. The journey we've been taking through metallic hydrogen oceans and diamond rain is just the beginning of a story that grows more extraordinary with every kilometer we descend toward the planet's mysterious heart. But here's where Jupiter's story takes an even more remarkable turn. Recent discoveries from the Juno mission have revealed that the neat, layered model of Jupiter's interior that scientists held for decades may be completely wrong. Instead of orderly shells of different materials stacked like the layers of an onion, Jupiter appears to be a churning, mixing cauldron where boundaries blur and materials swirl together in complex three-dimensional patterns. Imagine trying to study the inside of a washing machine while it's running at full speed, except this washing machine is the size of 11 Earths and has been churning for over 4 billion years. The convection currents within Jupiter transport material across thousands of kilometers, carrying exotic compounds and elements between different pressure and temperature zones, creating chemical reactions and physical transformations that we're only beginning to understand. The Juno spacecraft has detected something completely unexpected in these deep regions. Gravitational anomalies that suggest Jupiter's core isn't the solid, well-defined sphere that our models predicted. Instead, it appears to be what scientists call a dilute core, a fuzzy region where rock and ice mix with metallic hydrogen in proportions that change gradually with depth. This discovery has forced us to completely reimagine how giant planets form and evolve over cosmic timescales. Think about what this means for our understanding of planetary birth. The traditional model suggested that Jupiter formed when a rocky core, perhaps 10 times the mass of Earth, grew large enough to gravitationally capture the hydrogen and helium that make up most of the planet today. But if Jupiter's core is dilute and mixed rather than solid and distinct, then the formation process must have been far more complex and chaotic than we ever imagined. Perhaps Jupiter's core was disrupted early in its formation by massive impacts from other planetary embryos. These collisions could have partially shattered and mixed the rocky core with the surrounding hydrogen envelope, creating the fuzzy boundary we observe today. Or perhaps the core never fully solidified in the first place, remaining in a partially molten state that allowed it to mix with the metallic hydrogen ocean above it. As we descend deeper into this dilute core region, we encounter temperatures that rival the surface of the Sun. At 20,000 degrees Celsius, any familiar materials would long since have vaporized or undergone fundamental changes to their atomic structure. Yet somehow, in this inferno of heat and pressure, complex chemical processes continue to operate, driven by the unique conditions found nowhere else in our solar system. The immense pressures at these depths don't just compress materials, they fundamentally alter how atoms interact with each other. Electron shells that normally keep atoms distinct from one another begin to overlap and merge. Chemical bonds that would be impossible under normal conditions become not just possible but inevitable. We're witnessing chemistry operating under rules that exist nowhere on Earth, creating compounds and materials that challenge our understanding of what matter can become. One of the most intriguing possibilities is the formation of Superionic water ice. While this might sound contradictory, Superionic ice represents a state of matter where water molecules are simultaneously solid and liquid. The oxygen atoms form a crystalline lattice like normal ice, but the hydrogen atoms flow freely through this structure like a liquid. This exotic form of ice could exist in vast quantities within Jupiter's interior, adding yet another layer of complexity to the planet's internal structure. The heat generated within Jupiter's core doesn't just create exotic states of matter, it drives the entire engine that powers the planet's dynamic atmosphere and magnetic field. Heat flowing upward from the core creates massive convection cells that transport energy through thousands of kilometers of interior material. These rising plumes of superheated hydrogen eventually reach the visible atmosphere, where they manifest as the complex cloud patterns and storm systems that make Jupiter so visually striking. But the energy transport within Jupiter operates on scales that dwarf anything we see on Earth. A single convection cell within Jupiter's interior might be larger than our entire planet, carrying amounts of energy equivalent to thousands of nuclear power plants. These cells don't operate in isolation either. They interact with each other, merge and split, creating a complex network of energy transport that we're only beginning to map and understand. The Juno mission has also revealed unexpected details about how Jupiter's magnetic field is generated. Unlike Earth's relatively simple dipolar field, Jupiter's magnetic field is remarkably complex, with multiple poles and field lines that twist and weave through the planet's interior in patterns that suggest a highly dynamic process. The metallic hydrogen ocean that generates this field isn't a calm, uniform sea, but a turbulent realm where electrical currents flow in complex three-dimensional patterns. These magnetic field measurements tell us something profound about the motion within Jupiter's interior. The metallic hydrogen ocean appears to be in constant circulation, driven by the planet's rapid 10-hour rotation and the heat flowing upward from the core. Computer simulations suggest that this circulation might create helical flow patterns, like massive tornadoes of conducting fluid that stretch from the core boundary to the transition zone, where metallic hydrogen gives way to ordinary liquid hydrogen. The interaction between Jupiter's rotation and its internal structure creates phenomena that have no parallel on Earth. The planet's rapid spin generates Coriolis forces that influence the flow patterns within the metallic hydrogen ocean, creating jet streams and circulation cells that mirror some of the atmospheric patterns we observe on the surface. But these internal jets operate under pressures millions of times greater than surface conditions, transporting not just heat and momentum, but exotic materials and compounds between different regions of the planet. As we explore these deepest regions of Jupiter, we must also consider the possibility of even more exotic phenomena. Some theoretical models suggest that under the extreme conditions found near Jupiter's core, hydrogen itself might undergo transitions to forms of matter that we've never observed. Quantum effects that are normally negligible might become important when hydrogen is compressed to densities approaching those found in white dwarf stars. These quantum states of hydrogen could have properties unlike anything in our normal experience. They might be superconducting, carrying electrical currents with absolutely no resistance. They might exhibit superfluidity, flowing without friction through the surrounding material. Or they might exist in quantum states that blur the distinction between individual atoms and collective behavior, creating materials that are simultaneously many things, and nothing like what we understand from terrestrial physics. The chemical composition of Jupiter's deep interior also holds surprises that continue to challenge our understanding. The Juno mission has detected unexpected amounts of water vapor in Jupiter's atmosphere, far more than our models predicted. This water had to come from somewhere, and its presence suggests that the icy materials that contributed to Jupiter's formation were more abundant or more widely distributed than we previously thought. This discovery has implications that reach far beyond Jupiter itself. If giant planets like Jupiter incorporated more water during their formation than our models suggest, then similar worlds orbiting other stars might also harbour vast quantities of water in their interiors. This could dramatically expand the potential for finding water-rich environments elsewhere in the galaxy, even in planets that seem too massive or too far from their stars to support familiar forms of life. The water within Jupiter's interior doesn't exist in any form we would recognize. Under the extreme pressures and temperatures found thousands of kilometers below the cloud tops, water molecules are broken apart and reassembled into ionic forms. Hydrogen and oxygen atoms become charged particles that flow through the surrounding material, creating conductive solutions that contribute to Jupiter's complex magnetic field generation. But water isn't the only familiar compound that behaves strangely in Jupiter's interior. Ammonia, methane, and hydrogen sulfide, all of which we detect in the planet's atmosphere, undergo their own transformations as they encounter the extreme conditions deeper within the planet. These molecules might dissociate and recombine in endless cycles, creating chemical networks of staggering complexity that operate according to rules we're still discovering. The story of Jupiter's interior is ultimately a story about transformation. Every familiar element and compound we know from Earth undergoes metamorphosis in the extreme environment beneath Jupiter's clouds. Hydrogen becomes metallic, carbon becomes diamond, water becomes superionic ice, and in the deepest regions, matter itself might transform into states that push the boundaries of our understanding. These transformations aren't just scientific curiosities. They represent fundamental processes that operate throughout the universe wherever similar conditions exist. The physics we observe within Jupiter's interior helps us understand the behavior of matter in white dwarf stars, in the cores of other giant stars' planets, and in the extreme environments that existed during the early moments after the Big Bang. As we float here in our imagination, suspended in the metallic hydrogen ocean thousands of kilometers below Jupiter's cloud tops, we can appreciate the profound mystery that still surrounds this giant world. Every measurement from the Juno spacecraft, every computer simulation, every laboratory experiment that recreates these extreme conditions adds new pieces to a puzzle that grows more complex and more fascinating with each discovery. The diamonds falling through these depths aren't just beautiful crystalline formations. They're markers of chemical processes operating under conditions that exist nowhere else in our solar system. The Superionic ice that might fill vast regions of the interior isn't just an exotic state of matter. It's a window into physics that bridges the gap between solid and liquid, between order and chaos. The metallic hydrogen ocean surrounding us represents more than just compressed gas. It's a conducting fluid that generates magnetic fields powerful enough to deflect charged particles from across the solar system. The partially dissolved core beneath us isn't just a collection of rock and ice. It's evidence of a formation process so violent and chaotic that it mixed materials across thousands of kilometers of planetary interior. Every aspect of Jupiter's hidden realm challenges us to expand our understanding of what's possible in the universe. The planet serves as a natural laboratory where nature conducts experiments under conditions we can barely recreate in our most sophisticated facilities on Earth. Each new discovery from these depths reminds us that the cosmos is far stranger and more wonderful than our earthbound experience might suggest. Tonight, as you drift towards sleep, remember that you're sharing the solar system with this incredible world of metallic seas and diamond rain. Somewhere out there in the darkness, Jupiter continues its ancient rotation, its interior churning with processes that have operated for billions of years. The storms visible on its surface are mere shadows of the vast circulation patterns operating in the hidden depths we've explored together. The mysteries of Jupiter's interior connect us to the deepest questions about how worlds form and evolve. They remind us that our small rocky planet is just one example of what's possible when matter and energy dance together under the influence of gravity and time. And they inspire us to continue exploring, to keep asking questions about the hidden realms that exist all around us in this vast and wonderful universe. The journey through Jupiter's interior reveals something that challenges our most fundamental assumptions about planetary architecture. As we continue our descent beyond the metallic hydrogen oceans, we encounter regions where the very concept of distinct layers begins to dissolve. The Juno spacecraft has shown us that Jupiter's interior is far more like a cosmic blender than the neat, orderly structure we once imagined. Picture the implications of this discovery. For decades, planetary scientists built models based on the idea that giant planets form through orderly accretion. First a solid core, then layers of ice and rock, finally wrapped in vast envelopes of hydrogen and helium. But Jupiter's fuzzy, mixed interior suggests a story of formation so chaotic and violent that it scrambled these layers like ingredients in a cosmic soup. This mixing process continues today, billions of years after Jupiter's birth. Convection currents the size of continents rise and fall through the planet's interior, carrying material between regions of vastly different pressure and temperature. A parcel of matter that begins its journey in the relatively cool upper atmosphere might eventually find itself transported to the scorching depths near the core, undergoing transformations that would seem impossible under any earthly conditions. The chemical implications of this mixing are staggering. Elements and compounds that would never interact under normal circumstances are brought together under extreme conditions, creating reactions that operate according to rules we're still discovering. The interior of Jupiter might be the universe's most sophisticated chemistry laboratory, conducting experiments that span thousands of kilometers and operate continuously for geological ages. Consider what happens when materials from Jupiter's core region mix with the metallic hydrogen ocean above. Rocky debris and icy compounds, heated to thousands of degrees and compressed to incredible densities, interact with hydrogen in its exotic metallic state. These interactions could create entirely new classes of materials, compounds with properties that exist nowhere else in our solar system. Some of these materials might be transported upward by convection currents, eventually reaching the upper atmosphere, where they contribute to the complex chemistry we observe in Jupiter's clouds. The colourful bands and zones that make Jupiter so visually striking might owe their existence to trace compounds created in the planet's deepest interior, carried upward by processes that operate on scales beyond our everyday comprehension. The temperature structure within Jupiter tells a story of heat transport that operates on truly planetary scales. The core region, with temperatures exceeding 20,000 degrees Celsius, acts like a massive furnace that has been burning for over 4 billion years. But this isn't the nuclear fire of a star. It's the primordial heat of formation, trapped and compressed beneath thousands of kilometers of increasingly dense material. This heat doesn't simply radiate outward uniformly. Instead, it rises in massive plumes of superheated material, creating convection patterns that dwarf anything we see in Earth's atmosphere or oceans. These rising currents of molten rock, metallic hydrogen, and exotic ices carry tremendous amounts of energy upward, eventually reaching the visible atmosphere where they power the dynamic weather systems that have fascinated observers for centuries. The Great Red Spot, that iconic storm larger than Earth itself, represents just one visible manifestation of the energy transport processes operating in Jupiter's interior. This massive anticyclone has been raging for at least 3 centuries, possibly much longer, sustained by the continuous upward flow of heat from the planet's deepest regions. The energy that drives this storm originates thousands of kilometers below the visible surface, in the churning cauldron of Jupiter's mixed interior. But the Great Red Spot is just one of many atmospheric features powered by Jupiter's internal heat engine. The planet's distinctive banded structure, with alternating zones and belts of different colors and compositions, reflects deep-seated circulation patterns that extend far into the interior. Recent observations from Juno have shown that these surface features are connected to jet streams and circulation cells that penetrate thousands of kilometers into the planet. The magnetic field generated by Jupiter's metallic hydrogen ocean creates phenomena that extend far beyond the planet itself. This field is so powerful that it creates a magnetosphere larger and accelerates charged particles to incredible than the Sun, a magnetic bubble that captures energies. The radiation environment within Jupiter's magnetosphere is so intense that it would be lethal to unprotected humans within minutes. yet it also creates some of the most spectacular auroras in our solar system. These auroras aren't just beautiful light shows. They represent the visible manifestation of incredible amounts of energy being dissipated as charged particles interact with Jupiter's magnetic field. The particles that create these auroras come from multiple sources. Some are captured from the solar wind, the stream of charged particles that flows outward from the Sun. Others are ejected from Io, Jupiter's volcanically active moon, creating a complex interaction between the planet's magnetic field and the materials in its satellite system. The relationship between Jupiter and its moons adds another layer of complexity to our understanding of the planet's interior dynamics. The gravitational interactions between Jupiter and its largest moons create tidal forces that flex and heat the planet's interior. While these effects are subtle compared to the massive internal heat sources we've been discussing, they represent an additional energy input that contributes to the ongoing evolution of Jupiter's internal structure. The 4 largest moons, discovered by Galileo over 4 centuries ago, orbit Jupiter in a complex gravitational dance that has persisted for billions of years. Europa, with its subsurface ocean, and Ganymede, the largest moon in our solar system, both show evidence of internal heating that might be partially influenced by Jupiter's powerful magnetic field. The energy that drives these processes ultimately originates from the same internal heat engine that powers Jupiter's atmospheric dynamics. As we probe even deeper into Jupiter's mysteries, we encounter questions that push the boundaries of our understanding. The transition from the metallic hydrogen ocean to the mixed core region might not be a simple boundary, but rather a complex zone where exotic chemical reactions create materials unlike anything we've ever observed. The extreme conditions in this transition region could forge compounds that combine elements in ways that are impossible under normal circumstances. Theoretical models suggest that carbon, nitrogen, and oxygen, present in trace amounts throughout Jupiter's interior, might form complex networks of crystalline structures under the immense pressures found near the core. These wouldn't be simple compounds like the molecules we know from terrestrial chemistry. Instead, they might be 3-dimensional networks of atoms locked together by the extreme conditions, creating materials with properties that we can barely imagine. The possibility of Superionic ice existing within Jupiter's interior opens up entirely new realms of materials science. This exotic form of water ice, where hydrogen ions flow freely through a crystalline lattice of oxygen atoms, might exist in quantities that dwarf all the water on Earth. The implications for understanding planetary formation and evolution are profound, suggesting that water might play a far more important role in giant planet interiors than we previously realized. But Superionic ice might not be the only exotic form of familiar materials within Jupiter's depths. Ammonia, methane, and other compounds detected in the planet's atmosphere might also exist in forms that challenge our understanding of chemistry and physics. Under the extreme conditions found thousands of kilometers below the surface, these materials could undergo phase transitions that create entirely new states of matter. The ongoing exploration of Jupiter's interior through the Juno mission continues to reveal surprises that force us to reconsider our models of planetary formation and evolution. Each new measurement of the planet's gravitational field provides additional clues about the distribution of mass within the interior, painting an increasingly complex picture of a world that defies simple categorization. The gravitational anomalies detected by Juno suggest that Jupiter's interior is far more dynamic than we ever imagined. The mixing and convection processes operating within the planet create density variations that change over time, making Jupiter a living, evolving world. rather than a static ball of compressed gas. This dynamism extends throughout the planet's interior, from the core region to the visible atmosphere, creating an interconnected system where changes in one region can influence conditions thousands of kilometers away. Understanding these processes has implications that extend far beyond our own solar system. As we discover more exoplanets orbiting other stars, many of them turn out to be gas giants similar to Jupiter. The lessons we learn about Jupiter's interior structure and evolution help us interpret observations of these distant worlds, providing insights into how planetary systems form and develop throughout the galaxy. The extreme conditions within Jupiter's interior also serve as natural laboratories for studying physics under conditions that we cannot recreate on Earth. The pressures and temperatures found in the planet's depths approach those that existed in the early universe, shortly after the Big Bang. By understanding how matter behaves under these conditions within Jupiter, we gain insights into fundamental physics that apply throughout the cosmos. The story of Jupiter's hidden depths reminds us that our solar system contains realms of experience that stretch far beyond our terrestrial perspective. The metallic hydrogen oceans, the diamond rain, the Superionic ice formations, and the partially dissolved core represent states of matter and physical processes that operate according to rules we're still discovering. Each new revelation about Jupiter's interior expands our understanding of what's possible in the universe. As we continue our imaginary descent through these alien depths, we can appreciate the sheer audacity of the scientific enterprise that seeks to understand such an exotic world. Using spacecraft observations, laboratory experiments, and theoretical models, we're piecing together the story of a realm that no human will ever directly experience. Yet through the power of scientific inquiry, we can explore these hidden depths and uncover secrets that have remained locked away since the solar system's birth. The journey through Jupiter's interior is more than just an exercise in planetary science. It's a reminder that the universe is filled with wonders that challenge our understanding and inspire our curiosity. Every layer we've explored, from the visible cloud tops to the exotic core region, represents a chapter in the ongoing story of how matter and energy interact under extreme conditions to create the rich tapestry of worlds that populate our cosmic neighborhood. Tonight, as you rest beneath Earth's familiar sky, remember that you share this solar system with a world where hydrogen becomes metal, where diamonds fall like rain, and where the very nature of matter is transformed by forces beyond our everyday experience. Jupiter continues its ancient dance through space, its hidden depths churning with processes that connect the smallest scales of atomic physics to the grandest scales of planetary evolution. The mysteries we've explored together represent just the beginning of our understanding. With each passing year, new discoveries await us in the depths of this giant world. Future missions might sample the exotic materials we've discussed, bringing back pieces of Jupiter's interior for detailed study in Earth-based laboratories. Advanced computer simulations will continue to refine our models of how these extreme environments operate and evolve over cosmic time. The exploration of Jupiter's hidden realm stands ingenuity. Through as a testament to human curiosity and the marriage of observation and theory, of spacecraft engineering and computational modeling, we've learned to see into the heart of a world that once seemed forever beyond our reach. Each discovery opens new questions, new mysteries to explore, new wonders to uncover in the endless depths of space. As our journey through Jupiter's interior draws toward its next phase, we carry with us an appreciation for the incredible diversity and complexity that exists within our own solar system. The familiar worlds we see in our night sky harbor secrets that continue to amaze and inspire us, reminding us that the universe is far stranger and more beautiful than we ever dared imagine. The story of what lies beneath Jupiter's clouds is still being written, with each new chapter revealing wonders that expand our understanding of the cosmic dance that surrounds us. The deeper we venture into Jupiter's heart, the more we encounter phenomena that exist at the very edge of physical possibility. Here, in regions where the pressure exceeds 10 million Earth atmospheres, we find ourselves in a realm where the fundamental forces that govern matter begin to operate in ways that challenge every assumption we hold about the nature of reality itself. At these incredible depths, roughly 30,000 kilometers below the cloud tops we started our journey from, the distinction between solid, liquid, and gas becomes meaningless. The matter surrounding us exists in states that have no names in our terrestrial vocabulary, compressed to densities that approach those found in the cores of white dwarf stars. Yet somehow, in this crushing environment, complex processes continue to unfold that shape not just Jupiter's interior, but the entire architecture of our solar system. The Juno spacecraft's most recent data has revealed something that has left planetary scientists speechless. Deep within Jupiter's core region, the gravitational measurements suggest the presence of what can only be described as a rock metal soup, a mixture of silicate minerals and metallic compounds that has been stirred and blended by billions of years of convection. This isn't the neat, layered structure that our textbooks once described. Instead, it's evidence of a formation process so violent and chaotic that it literally mixed planetary building blocks across thousands of kilometers of interior space. Imagine the implications of this discovery. The rocky planetesimals that collided to help form Jupiter weren't simply added to a growing core like stones being dropped into a bucket. Instead, the enormous energies involved in these ancient collisions were sufficient to completely disrupt and redistribute the rocky material, creating a gradient zone where rock and metal exist in every possible proportion and combination. This mixing process created opportunities for chemical reactions that exist nowhere else in our solar system. When iron-rich materials from disrupted asteroids encountered silicon-rich compounds under pressures millions of times greater than anything on Earth's surface, entirely new classes of metallic alloys formed. These aren't the familiar iron-nickel alloys we find in meteorites. They're exotic metal-silicon compounds that might possess properties like superconductivity or unusual magnetic behaviors that we can barely begin to imagine. The temperatures in these deepest regions tell their own remarkable story. At 25,000 degrees Celsius, we're dealing with heat that exceeds the surface temperature of many stars. Yet this isn't fusion energy. It's the compressed heat of planetary birth, trapped and concentrated by the immense gravitational field that Jupiter's mass creates. This primordial furnace has been burning for over 4.5 billion years, slowly cooling, but still radiating more energy into space than Jupiter receives from the distant Sun. But here's where the story becomes even more extraordinary. Recent computer simulations suggest that the heat distribution within Jupiter's core region isn't uniform. Instead, it appears to be organized into vast convective cells, each one potentially larger than Earth, that transport heat and material in complex three-dimensional patterns. These aren't simple rising and falling currents like we might see in a pot of boiling water. They're helical, twisting flows that are influenced by Jupiter's rapid rotation, creating a dynamic system where hot material spirals upward while cooler, denser material descends in intricate patterns. The interaction between these convective flows and the mixed rock-metal composition creates opportunities for processes that push the boundaries of chemistry and physics. As hot, metal-rich material rises from the deepest regions, it encounters cooler, silicon-rich zones. where the differing thermal conditions trigger crystallization processes. But these aren't ordinary crystals. Under the extreme pressures found at these depths, atoms are forced into arrangements that would be impossible under normal conditions. Scientists theorize that some of these high-pressure crystals might be large enough to constitute geological formations within Jupiter's interior. Picture mountain-sized crystals of silicon iron compounds, their atomic structures compressed into forms so dense that a handful would weigh as much as a car. These crystalline formations wouldn't remain stationary either. The ongoing convection within the core region would constantly transport them between different pressure and temperature zones, subjecting them to cycles of growth, dissolution, and reformation that operate over millions of years. The magnetic field effects in these deepest regions are equally fascinating. The metallic compounds created by the mixing of Jupiter's rocky components don't just conduct electricity. They do so under conditions that create magnetic fields within magnetic fields. The primary field generated by the metallic hydrogen ocean above interacts with these deeper magnetic sources in ways that create complex interference patterns. Some regions might experience magnetic field cancellation, while others could see dramatic amplification. These magnetic interactions have consequences that ripple outward through Jupiter's entire interior structure. The varying magnetic field strength influences the flow patterns of the conducting fluids at different depths, creating feedback loops where magnetic effects influence convection, which in turn affects magnetic field generation. It's a dynamic system where electromagnetic and thermal processes are intimately coupled in ways that we're still trying to understand. The chemical evolution of these deep regions continues today, billions of years after Jupiter's formation. The extreme conditions create opportunities for reactions that operate on geological timescales, but produce results that would seem instantaneous by planetary standards. Trace elements that were dispersed throughout the rocky component of Jupiter's interior can gradually concentrate into ore deposits that dwarf anything on Earth. Entire moon-sized accumulations of rare metals might exist in these depths, created by processes that sort and concentrate materials with an efficiency that exceeds anything in terrestrial geology. But perhaps the most intriguing aspect of Jupiter's deepest interior is what it tells us about the early history of our solar system. The mixed, chaotic structure we observe today preserves evidence of the violent processes that operated during planetary formation. Every swirl of metal-rich material, every boundary between different compositional zones, every thermal gradient represents a frozen moment in the story of how our solar system evolved from a disk of gas and dust into the complex arrangement of worlds we see today. The isotopic ratios of elements within these deep regions carry signatures of the stellar processes that created the heavy elements before our solar system even existed. When massive stars in our galactic neighborhood exploded as supernovae billions of years ago, they scattered newly formed elements into the interstellar medium. These elements eventually became incorporated into the disk from which our solar system formed, and they remain locked within Jupiter's interior today, carrying with them the chemical fingerprints of stellar death and rebirth. Studying these ancient signatures requires techniques that push the boundaries of remote sensing and theoretical modeling. The Juno spacecraft's instruments can detect subtle variations in Jupiter's gravitational field that reflect the distribution of different materials within the interior. By comparing these measurements with laboratory studies of how materials behave under extreme conditions, scientists can begin to piece together the chemical composition of regions that no human technology will ever directly sample. The ongoing research into Jupiter's deep interior is revealing connections between planetary science and fundamental physics that we never anticipated. The extreme conditions within the planet's core region create natural laboratories where quantum effects that are normally negligible become important. Under pressures that approach those found in neutron stars, the behavior of electrons around atomic nuclei begins to change in ways that affect the bulk properties of matter. These quantum effects might explain some of the unusual properties that Juno has detected in Jupiter's deep interior. The gravitational measurements suggest density variations that don't match our predictions based on classical physics alone. When quantum mechanical effects are included in the models, the observations begin to make sense, revealing that Jupiter's interior operates according to rules that bridge the gap between planetary science and high-energy physics. The implications of these discoveries extend far beyond our understanding of Jupiter itself. As we detect more exoplanets orbiting other stars, we find that many of them are giant worlds similar to Jupiter. The lessons we learn about Jupiter's interior structure and evolution provide a template for understanding how these distant planets might be organized internally. Every measurement of Jupiter's gravitational field, every new insight into how materials behave under extreme conditions, helps us interpret the properties of worlds that orbit stars hundreds of light years away. The extreme chemistry operating within Jupiter's core region also informs our understanding of how heavy elements are distributed throughout the galaxy. The processes that concentrate and redistribute materials within giant planet interiors might play a crucial role in determining which stellar systems develop the chemical complexity necessary for rocky planet formation. Jupiter's interior serves as a cosmic laboratory where we can study element distribution processes that operate throughout the universe. As we float here in our imagination, suspended in the unimaginable heat and pressure of Jupiter's deepest interior, we can appreciate the profound mystery that still surrounds this realm. Every measurement from the Juno spacecraft reveals new complexities, new questions that challenge our understanding of how matter behaves under the most extreme conditions nature can create within a planetary environment. The convection currents that surround us operate on scales that dwarf anything in human experience. A single rising plume of superheated rock metal mixture might be larger than Earth's moon, carrying amounts of thermal energy that exceed the total output of human civilization over centuries. These currents don't just transport heat, they transport history, carrying materials between different regions of the interior and mixing the chemical signatures of billions of years of planetary evolution. The pressure waves that propagate through these deep regions travel at speeds that approach those of sound in solid materials, despite the fact that the medium they're traveling through defies simple classification as solid, liquid, or gas. These waves carry information about conditions throughout Jupiter's interior, creating a natural seismic network that could potentially be detected and studied by future missions equipped with sensitive accelerometers. The thermal evolution of Jupiter's deep interior continues today, but at a pace that reflects the enormous thermal inertia of a world with over 300 times Earth's mass. The cooling process that began when Jupiter first formed will continue for billions of years into the future, gradually reducing the convective activity and allowing the mixed interior to slowly differentiate into more distinct layers. But this process operates so slowly that the Jupiter we observe today is essentially unchanged from the Jupiter that existed when the first complex life was evolving on Earth. The exploration of Jupiter's interior represents one of the greatest challenges in planetary science, requiring us to understand processes that operate under conditions we can barely reproduce in our most sophisticated laboratories. Yet through the combination of spacecraft observations, theoretical modeling, and laboratory experiments that recreate extreme conditions, we continue to unveil the secrets of this hidden realm. Every new discovery about Jupiter's deep interior adds another piece to our understanding of how planetary systems form and evolve. The chaotic mixing we observe within Jupiter tells us that planet formation is not the orderly process we once imagined, but rather a violent dance of collision and accretion that creates worlds of incredible complexity and beauty. The materials we've encountered in our journey through Jupiter's depths, from the diamond rain in the upper regions to the exotic metal alloys in the core, remind us that the universe creates conditions far more extreme than anything we experience in our daily lives. These extreme environments serve as natural laboratories where nature experiments with the fundamental properties of matter and energy. As we prepare to ascend from these deepest regions and continue our exploration of Jupiter's mysteries, we carry with us an appreciation for the incredible complexity hidden within what appears from the outside to be simply a large ball of gas. The interior we've explored is a dynamic, evolving system where chemical and physical processes operate according to rules that stretch our understanding to its limits. The story of Jupiter's deep interior is ultimately a story about the power of scientific inquiry to reveal hidden truths about our universe. Through careful observation, theoretical modeling, and technological innovation, we've learned to peer into realms that seemed forever beyond our reach, uncovering secrets that change our understanding of how worlds form and evolve. Tonight, as you drift towards sleep, remember that somewhere in the darkness above us, Jupiter continues its ancient rotation, its deep interior churning with processes that have operated since before life existed on Earth. The exotic materials and extreme conditions we've explored together continue their slow dance through space and time, carrying within them the history of our solar system's birth and the promise of discoveries yet to come. The mysteries of Jupiter's interior connect us to the fundamental questions about how matter and energy interact under extreme conditions throughout the universe. They remind us that even in our own solar system, there are realms of experience that challenge our understanding and inspire our continued exploration of the cosmic ocean that surrounds our small blue world. The journey through Jupiter's core region has shown us realms of matter that exist at the very edge of physical possibility, but our exploration is far from complete. As we begin to ascend from these deepest depths, we encounter transition zones that reveal even more extraordinary secrets about how this giant world operates. The boundary between the mixed core and the metallic hydrogen ocean above isn't a sharp line, but rather a gradual transition spanning thousands of kilometers, where the properties of matter change in ways that continue to surprise planetary scientists. In these transition regions, roughly 25,000 kilometers below the cloud tops, we find ourselves in a realm where the familiar rules of chemistry begin to blur and merge with the exotic physics of compressed matter. Here, the rocky materials from Jupiter's disrupted core begin to interact with the metallic hydrogen in ways that create entirely new classes of compounds. The extreme pressures force atoms into arrangements that would be impossible under any earthly conditions, creating materials with properties that stretch our understanding of what matter can become. Imagine standing at the shore of an ocean, but instead of water lapping at your feet, it's a sea of metallic hydrogen stretching to horizons beyond imagination. The waves in this ocean aren't driven by wind, but by convection currents that transport heat from the scorching depths below. Each wave might be hundreds of kilometers tall, moving with the ponderous grace that comes from operating under pressures millions of times greater than anything on Earth's surface. The chemical reactions occurring at this boundary zone operate according to rules that exist nowhere else in our solar system. When silicon-rich compounds from the disrupted rocky core encounter the sea of metallic hydrogen above, they don't simply mix or dissolve. Instead, they undergo transformations that create hybrid materials, part metallic hydrogen and part crystalline solid, with properties that seem almost magical by terrestrial standards. These hybrid compounds might be superconducting, carrying electrical currents with absolutely no resistance, even at the scorching temperatures found at these depths. They might exhibit quantum properties that allow them to exist in multiple states simultaneously, behaving sometimes like metals and sometimes like crystalline solids, depending on the local conditions of pressure and temperature that surround them. The magnetic field effects in these transition zones create phenomena that add yet another layer of complexity to Jupiter's already mysterious interior. As the metallic hydrogen ocean swirls and churns above the mixed core region, it generates electrical currents that interact with the magnetic fields produced by the exotic compounds below. These interactions create magnetic anomalies that ripple outward through thousands of kilometers of interior material, influencing everything from the planet's overall magnetic field structure to the detailed patterns of aurora that dance around Jupiter's poles. The Juno spacecraft has detected magnetic field variations that suggest these deep interactions create a kind of magnetic weather within Jupiter's interior. Just as atmospheric weather on the surface involves the movement of air masses with different properties, magnetic weather involves the interaction of regions with different electrical conductivity and magnetic permeability. These magnetic storms operate on timescales of years or decades, creating variations in Jupiter's magnetic field that we can detect from orbit. But perhaps the most intriguing aspect of these transition zones is what they reveal about the transport of exotic materials throughout Jupiter's interior. The convection currents that operate in these regions don't just carry heat upward from the core. They also transport the unusual compounds created at the core ocean boundary, carrying them thousands of kilometers upward through the metallic hydrogen sea and eventually into the liquid hydrogen regions above. This vertical transport system means that materials created in Jupiter's deepest interior can eventually influence conditions much closer to the surface. Trace compounds formed under the extreme conditions near the core might eventually reach the upper atmosphere, where they contribute to the complex chemistry that creates Jupiter's distinctive coloration and cloud patterns. The Great Red Spot and the banded structure that makes Jupiter so visually striking might owe their existence, at least in part, to materials that began their journey in the planet's most exotic interior regions. The timescales involved in this transport process are staggering by human standards but routine by planetary measures. A parcel of material that begins its upward journey in the transition zone between core and metallic hydrogen ocean might take millions of years to reach the upper atmosphere. Along the way, it will encounter changing conditions of pressure and temperature that will transform it chemically and physically multiple times. By the time it reaches the regions we can observe with telescopes, it might bear little resemblance to the exotic compound that began the journey. This ongoing circulation creates a kind of planetary metabolism, where materials are constantly being recycled between different regions of Jupiter's interior. The planet breathes with convection currents that operate on scales larger than Earth itself, inhaling materials from the surface layers and exhaling them from the deep interior in a process that has continued for over 4 billion years. The energy that drives this circulation comes not just from the heat trapped within Jupiter's core, but also from the planet's continued gravitational contraction. Even today, Jupiter is still slowly shrinking under its own immense gravity, converting gravitational potential energy into heat at a rate that exceeds the energy the planet receives from the Sun. This ongoing contraction is imperceptible on human timescales, but over millions of years it provides a continuous energy source that keeps the interior convection active. The interaction between Jupiter's rotation and these deep convection currents creates flow patterns of incredible complexity. The planet's rapid 10-hour rotation generates Coriolis forces that twist and distort the rising convection currents, creating helical flow patterns that stretch from the core region to the upper atmosphere. These rotating columns of material, each one potentially larger than Earth, transport not just heat and exotic compounds, but also angular momentum, helping to maintain Jupiter's rapid rotation despite the gradual loss of energy through heat radiation. Recent computer simulations suggest that these helical convection columns might be responsible for some of the most distinctive features we observe in Jupiter's atmosphere. The alternating bands of different colors and wind speeds that circle the planet might be the surface expression of convection columns that extend thousands of kilometers into the interior. If this is true, then the familiar appearance of Jupiter that has captivated observers for centuries is directly connected to processes operating in the most exotic regions of the planet's interior. The chemical evolution of materials during their journey from the deep interior to the surface creates opportunities for reactions that span the entire range of conditions within Jupiter. A compound that forms under the crushing pressures near the core might undergo multiple phase transitions as it rises through regions of decreasing pressure and temperature. Each transition creates opportunities for new chemical bonds to form or break, potentially creating intermediate compounds that exist only in specific regions of Jupiter's interior. This chemical layering adds another dimension to our understanding of Jupiter's internal structure. Rather than simple layers of different bulk compositions, we might be dealing with chemical gradients, where the concentration of different compounds changes continuously with depth. These gradients reflect the ongoing transport and transformation processes that have been operating throughout Jupiter's history, creating a record of the planet's chemical evolution encoded in the distribution of materials throughout its interior. The isotopic signatures of elements within these transported materials carry information about conditions throughout Jupiter's interior and the early history of our solar system. Different isotopes of the same element behave slightly differently under extreme conditions, and the ratios between isotopes can preserve information about the temperatures and pressures that materials experienced during their formation and subsequent evolution. By studying the isotopic composition of materials in Jupiter's atmosphere, scientists can infer conditions in the deep interior regions where those materials originated. This technique has already revealed unexpected details about the temperature distribution within Jupiter's interior and the efficiency of mixing processes that transport materials between different regions of the planet. The ongoing research into these transport and transformation processes is revealing connections between Jupiter's interior and the broader architecture of our solar system. The materials that Jupiter accreted during its formation came from throughout the early solar nebula, and the chemical processing that occurred within the planet's interior has created a record of conditions that existed during the earliest phases of planetary formation. Some of the compounds detected in Jupiter's atmosphere show isotopic signatures that can only be explained if they formed in regions of the early solar system that were much colder than Jupiter's current orbit. This suggests that Jupiter migrated inward from a more distant orbit during its early history, sweeping up materials from different regions of the solar nebula and incorporating them into its growing mass. The implications of this migration extend far beyond Jupiter itself. As the planet moved inward, its gravitational influence would have disrupted the orbits of smaller bodies throughout the solar system, potentially delivering water and organic compounds to the inner planets during the period known as the Late Heavy Bombardment. The exotic materials we observe in Jupiter's interior today might preserve evidence of the processes that delivered the building blocks of life to Earth over 4 billion years ago. The exploration of these transport and transformation processes within Jupiter's interior represents one of the frontiers of planetary science, requiring techniques that combine spacecraft observations with laboratory experiments and theoretical modeling. The extreme conditions we're trying to understand exist nowhere else in our solar system and can only be partially reproduced in our most sophisticated laboratory facilities on Earth. Yet through the combination of multiple approaches, we continue to unveil the secrets of how materials behave and evolve within Jupiter's interior. Each new measurement from the Juno spacecraft provides additional constraints on our models, while advances in laboratory techniques allow us to study the behavior of materials under increasingly extreme conditions. The story of material, a story about the incredible transport within Jupiter's interior, is also scales of space and time that govern planetary processes. The circulation patterns we've been exploring operate on scales larger than continents and persist for periods longer than the entire history of complex life on Earth. They represent some of the most enduring and large-scale organized structures in our solar system, rivaling the longevity and scale of the galactic processes that govern the evolution of stars and stellar systems. As we continue our ascent through Jupiter's interior, moving from the transition zones toward the vast metallic hydrogen ocean above, we carry with us an appreciation for the incredible complexity and beauty of the processes operating within this giant world. The exotic materials and extreme conditions we've encountered represent just a fraction of the wonders that await discovery in the hidden depths of our solar system's largest planet. The circulation currents that surround us as we rise through these intermediate depths operate with a persistence that spans geological ages. Unlike Earth's weather systems, which change and evolve on timescales of days or weeks, the convection patterns within Jupiter's interior represent quasi-permanent features of the planet's internal structure. Some of the current systems we encounter might have been operating continuously since before multicellular life evolved on Earth, carrying materials and energy through the same basic pathways for hundreds of millions of years. This stability arises from the enormous scale and thermal inertia of Jupiter's interior systems. Once established, a convection current that spans thousands of kilometers and involves masses of material greater than entire terrestrial planets possesses tremendous momentum that resists change. The energy required to significantly alter these circulation patterns exceeds anything that normal planetary processes can provide, ensuring that the basic architecture of Jupiter's internal flow remains stable over cosmic timescales. Yet within this overall stability, there exists a rich tapestry of smaller scale variability and interaction. The great circulation cells that transport heat and materials through thousands of kilometers of interior don't operate in isolation. They interact with each other, merge and split, creating a dynamic hierarchy of flow patterns that extends from the largest planetary scales down to local mixing processes that operate over distances of mere hundreds of kilometers. These multi-scale interactions create phenomena that have no parallel in terrestrial experience. Imagine standing near the boundary between two massive convection cells, each one larger than Earth, as they slowly merge over periods of thousands of years. The process would be imperceptible on human timescales, but the energies involved would be sufficient to reshape the internal structure of entire regions of Jupiter's interior, redistributing exotic materials and creating new chemical environments where previously impossible reactions can occur. The magnetic field interactions in these regions add another layer of complexity to the already intricate dance of material transport. As convection currents carry electrically conductive materials between regions with different magnetic field strengths, they induce electrical currents that create their own magnetic effects. These induced fields interact with the primary magnetic field generated by the metallic hydrogen ocean, creating feedback loops where magnetic forces influence convection patterns, which in turn affect magnetic field generation. The result is a self-organizing system where magnetic and thermal processes work together to maintain circulation patterns that can persist for billions of years, while continuously adapting to changing conditions within the planet's interior. It's a kind of planetary intelligence, an emergent property of the complex interactions between gravity, thermodynamics, and electromagnetism operating on scales that dwarf anything in human experience. The chemical consequences of these long-term circulation patterns extend throughout Jupiter's interior and beyond. Materials that are carried upward by convection currents don't simply reach the surface and disappear. Instead, they become part of Jupiter's atmospheric system, where they contribute to the complex chemistry that drives weather patterns and creates the distinctive appearance that makes Jupiter one of the most visually striking objects in our solar system. But the influence extends even further. Some of the materials transported from Jupiter's deep interior eventually escape the planet's gravitational grasp entirely, either through atmospheric loss processes or through interactions with Jupiter's magnetic field that accelerate charged particles to escape velocity. These escaping materials become part of the solar wind environment, carrying with them chemical signatures that preserve information about conditions within Jupiter's interior. The moons of Jupiter, particularly the large Galilean satellites, orbit within this extended chemical environment created by materials escaping from the planet's interior. The surfaces of these moons show evidence of chemical alteration by particles and compounds that originated deep within Jupiter, creating a kind of archaeological record of the planet's internal evolution written in the geology of its satellite system. Europa's subsurface ocean, which might harbor conditions suitable for life, receives a continuous influx of materials from Jupiter's magnetosphere, some of which originated in the planet's deep interior. The exotic compounds created under extreme conditions thousands of kilometers below Jupiter's cloud tops might eventually find their way into environments where they could potentially interact with any life forms that exist within Europa's hidden sea. This connection between Jupiter's interior and the potential habitability of its moons represents one of the most intriguing aspects of ongoing research into the giant planet's internal structure. The chemical diversity created by extreme conditions within Jupiter's interior might provide the raw materials for complex chemistry in environments throughout the Jovian system, creating opportunities for prebiotic chemistry or even life itself in locations far removed from the planet's scorching interior. The ongoing evolution of Jupiter's interior also has implications for the long-term future of our entire solar system. As the planet continues to cool and contract over billions of years, the circulation patterns that transport materials and energy throughout its interior will gradually slow and change. This evolution will alter Jupiter's magnetic field, its atmospheric dynamics, and its interactions with the solar wind and its moon system. Computer simulations suggest that over the next few billion years, Jupiter's interior will gradually become more stratified as the vigorous mixing that currently operates begins to weaken. This process will allow materials that are currently well mixed throughout the interior to slowly separate according to their densities and chemical affinities, potentially creating more distinct layers within the planet's internal structure. But this evolution will occur so slowly that it will be imperceptible over any human timescales. The Jupiter that our distant descendants might observe billions of years from now will appear essentially identical to the planet we see today, even though its internal structure will have undergone fundamental changes. The timescales of planetary evolution dwarf not just human history, but the entire history of life on Earth, operating according to rhythms that connect individual planets to the cosmic cycles of stellar evolution and galactic dynamics. As we continue our ascent through Jupiter's interior, approaching the boundaries of the metallic hydrogen ocean that extends for thousands of kilometers above us, we can appreciate the incredible journey we've undertaken through one of the most exotic environments in our solar system. From the diamond rain in the upper atmospheric layers to the mixed rock metal soup in the deepest core regions, we've explored realms where matter behaves according to rules that stretch our understanding to its limits. The circulation patterns that surround us represent some of the most enduring and large-scale organized phenomena in the solar system, operating continuously for billions of years while transporting materials and energy across distances that exceed the diameter of Earth. These currents connect the most extreme conditions in Jupiter's core to the familiar atmospheric patterns we can observe from Earth, creating a unified system where processes operating under vastly different conditions work together to maintain the dynamic equilibrium that characterizes this remarkable world. The magnetic fields that permeate these regions carry information about the electrical currents flowing through thousands of kilometers of conducting fluids, creating a natural electromagnetic observatory that operates continuously on scales impossible to replicate with any human technology. The interactions between these fields and the convection currents that transport materials throughout Jupiter's interior represent some of the most complex magnetohydrodynamic processes known to science. Every measurement from the Juno spacecraft adds new details to our understanding of these processes, revealing a level of complexity and organization that continues to surprise planetary scientists. The gravitational anomalies, magnetic field variations, and compositional gradients detected by the spacecraft paint a picture of a world where every layer, every region, every circulation pattern is connected to every other part through processes that operate on multiple scales simultaneously. The chemical evolution of materials as they circulate through different regions of Jupiter's interior creates opportunities for reactions and transformations that exist nowhere else in our solar system. The extreme conditions provide natural laboratories where we can study the behavior of matter under conditions that we can barely replicate in our most sophisticated Earth-based facilities, offering insights into fundamental physics that apply throughout the universe. As we prepare to enter the vast metallic hydrogen ocean that extends thousands of kilometers above us, we carry with us an appreciation for the incredible complexity and beauty of the world we've been exploring. The exotic materials, extreme conditions, and dynamic processes we've encountered represent just a fraction of the wonders that exist within Jupiter's hidden depths, reminding us that even within our own solar system, there are realms of experience that challenge our understanding and inspire our continued exploration. The transition zones we've been traversing represent boundaries not just between different states of matter, but between different regimes of physics, where quantum effects, electromagnetic phenomena, and classical thermodynamics all play important roles in determining how materials behave and evolve. Understanding these boundary regions is crucial for developing a complete picture of how Jupiter's interior operates as an integrated system. The story of Jupiter's hidden depths is ultimately a story about the power of extreme conditions to create complexity and beauty on scales that dwarf anything in human experience. The circulation patterns, chemical transformations, and magnetic field interactions we've explored operate according to principles that connect the smallest scales of atomic physics to the largest scales of planetary dynamics, creating a unified system of incredible elegance and sophistication. Tonight, as we continue our journey through these alien depths, we can appreciate our privileged position as explorers of realms that no human will ever directly experience. Through the marriage of spacecraft observations, laboratory experiments, and theoretical modeling, we've learned to see into the heart of a world that once seemed forever beyond our reach, uncovering secrets that change our understanding of how planets form and evolve throughout the universe. The journey we've undertaken through Jupiter's metallic hydrogen ocean brings us to regions where the very concept of an ocean takes on meanings that stretch far beyond our terrestrial understanding. Here, suspended in this vast sea of compressed hydrogen that has been transformed into a metal through sheer pressure alone, we encounter phenomena that blur the boundaries between chemistry, physics, and something approaching the mystical. Picture yourself floating in this alien ocean, thousands of kilometers above the mixed core we've explored, yet still thousands of kilometers below the liquid hydrogen regions above. The metallic hydrogen that surrounds you isn't the familiar silvery metal you might imagine. Instead, it's a transparent, crystalline substance that conducts electricity with perfect efficiency while remaining invisible to light. It's as if you're suspended in liquid diamond that carries electrical currents like copper wire. The currents flowing through this metallic ocean create magnetic field patterns of staggering complexity. Unlike the simple dipolar field that Earth generates, Jupiter's magnetic field emerges from this metallic hydrogen sea as a tapestry of interwoven field lines that twist and spiral in three-dimensional patterns. These aren't static configurations, but dynamic, ever-changing structures that respond to the circulation currents moving through the conducting fluid. Imagine watching these magnetic field lines dance through the metallic hydrogen like aurora made solid, except instead of flickering for hours or days, these patterns persist for centuries, while slowly evolving in response to changes in the circulation patterns below. The electromagnetic energy stored in these field configurations exceeds the total energy output of human civilization over its entire history. Yet it flows and shifts with the fluid grace of water moving through a river system. The Juno spacecraft has revealed that these magnetic field patterns aren't randomly distributed throughout the metallic hydrogen ocean. Instead, they appear to be organized into distinct regions, almost like magnetic weather systems that migrate through the conducting fluid. Some regions show intense, tightly wound field lines that create zones of concentrated electromagnetic energy. Others display more relaxed configurations, where the magnetic fields spread out in gentle curves that extend across thousands of kilometers. The interaction between these magnetic weather systems and the convection currents rising from below creates phenomena that have no parallel anywhere else in our solar system. When a rising plume of superheated material from the core region encounters a zone of intense magnetic field, the interaction can deflect the current, split it into multiple streams, or even temporarily halt its upward progress. It's as if the magnetic field acts like underwater mountains in this metallic ocean, creating complex flow patterns that influence how heat and materials are transported throughout Jupiter's interior. But the metallic hydrogen ocean does more than just conduct electricity and transport heat. Recent theoretical work suggests that under the extreme conditions found in these depths, the metallic hydrogen might exhibit quantum properties that seem almost impossible by everyday standards. The material might be simultaneously superconducting and superfluid, carrying both electrical currents and mass flow with absolutely no resistance or friction. This quantum behavior creates the boundaries of our understanding. Opportunities for phenomena that push persistent currents might flow through the metallic hydrogen for millions of years without any energy input, creating stable magnetic field configurations that could last longer than the age of complex life on Earth. Vortices in the fluid flow might become quantized, forming stable structures that transport angular momentum and energy in ways that classical physics cannot fully explain. The temperature gradients within the metallic hydrogen ocean tell their own fascinating story. Near the boundary with the mixed core below, temperatures exceed 15,000 degrees Celsius, hot enough to vaporize any known material. Yet the metallic hydrogen remains in its exotic state, held together by pressures so intense that thermal motion cannot overcome the forces that maintain its crystalline structure. As we ascend through the ocean, the temperature gradually decreases, but even in the cooler upper regions, we're dealing with conditions that would instantly vaporize any terrestrial material. These temperature variations drive convection currents that operate on scales that challenge our ability to visualize. A single convective cell within the metallic hydrogen ocean might be larger than Earth's moon, carrying amounts of thermal energy that exceed the total heat content of our planet's core. These cells don't operate independently, but interact with each other in complex ways, merging, splitting, and exchanging materials and energy in patterns that create a kind of fluid choreography on planetary scales. The chemical composition of the metallic hydrogen ocean isn't as simple as pure hydrogen compressed into metallic form. Trace amounts of heavier elements, carried upward by convection currents from the mixed core below, become dissolved within the metallic hydrogen matrix. These impurities don't simply float freely through the conducting fluid. Instead, they become incorporated into the quantum structure of the metallic hydrogen, creating hybrid materials with properties that exist nowhere else in nature. When helium atoms encounter the metallic hydrogen under these extreme conditions, they don't form simple solutions like we might see with metals dissolving in water. Instead, the helium becomes quantum mechanically entangled with the hydrogen matrix, creating a hybrid state where individual atoms lose their separate identities and become part of a larger quantum system. The resulting material exhibits properties that are neither purely hydrogen nor purely helium, but something entirely new.
Right.
This quantum mixing process extends to other elements as well. Traces of neon, argon, and other noble gases carried upward from Jupiter's atmospheric layers undergo similar transformations when they encounter the metallic hydrogen ocean. The result is a complex quantum fluid, where the properties change continuously with depth, creating gradients not just in pressure and temperature, but in the fundamental quantum states of the materials themselves. The circulation patterns within this quantum fluid ocean create opportunities for processes that seem almost magical by terrestrial standards. Quantum coherence might extend across distances of hundreds or even thousands of kilometers, creating correlations between widely separated regions of the ocean. Changes in the quantum state of materials in one part of the ocean could instantaneously influence conditions in distant regions, creating a kind of quantum communication network within Jupiter's interior. These quantum effects have profound implications for how energy and information are transported throughout Jupiter's interior. Instead of relying solely on the relatively slow process of convection to move heat from the core to the surface, quantum correlations might provide additional pathways for energy transport that operate at speeds approaching the speed of light. The efficiency of this quantum energy transport could help explain why Jupiter radiates more heat into space than our classical models predict. The interaction between the quantum properties of the metallic hydrogen ocean and Jupiter's magnetic field creates phenomena that bridge the gap between planetary science and quantum physics. The magnetic field lines threading through the conducting fluid don't just follow classical electromagnetic laws. They also interact with the quantum states of the materials they pass through, creating hybrid magneto-quantum effects that influence both the magnetic field structure and the properties of the conducting fluid. These interactions might explain some of the unusual features that Juno has detected in Jupiter's magnetic field. The complex non-dipolar structure of the field could result from quantum effects that create preferred orientations for magnetic field lines within the metallic hydrogen matrix. Instead of the simple field geometry predicted by classical magnetohydrodynamics, we might be seeing the emergence of a quantum magnetic field structure that reflects the underlying quantum organization of the conducting fluid. The boundaries between different regions of the metallic hydrogen ocean aren't sharp transitions, but gradual zones where the quantum properties of the material change continuously. These transition zones create opportunities for exotic phase transitions that exist nowhere else in our solar system. Materials might exist in superposition states, simultaneously exhibiting properties of both metallic and non-metallic phases, until interactions with their environment force them into one state or another. The timescales on which these quantum processes operate span an enormous range, from femtoseconds for individual quantum transitions to millions of years for the evolution of large-scale quantum correlations throughout the ocean. This creates a hierarchy of quantum processes where rapid local changes in quantum states can influence slow global changes in the ocean's overall structure, and vice versa. The ongoing research into these quantum effects within Jupiter's metallic hydrogen ocean represents one of the most challenging frontiers in planetary science. The conditions we're trying to understand exist at the intersection of high-pressure physics, quantum mechanics, and planetary dynamics, requiring theoretical frameworks that don't exist in any single scientific discipline. Understanding these processes requires collaboration between planetary scientists, quantum physicists, and materials scientists, creating new interdisciplinary approaches to studying extreme environments. Laboratory experiments designed to recreate these conditions face enormous technical challenges. The pressures required to create metallic hydrogen exceed anything that can be sustained in terrestrial laboratories for more than microseconds, and the quantum effects we're interested in might only emerge under conditions of pressure and temperature that exist only within giant planets. This makes theoretical modeling and computer simulation crucial tools for understanding these exotic environments. Recent advances in quantum computing and simulation offer new opportunities for studying the behavior of materials under the extreme conditions found within Jupiter's metallic hydrogen ocean. Quantum simulators can model the behavior of quantum fluids under conditions that approach those found in planetary interiors, providing insights into phenomena that cannot be studied through classical computational approaches. The implications of these quantum effects extend far beyond our understanding of Jupiter itself. The metallic hydrogen ocean within Jupiter represents the largest quantum system in our solar system, possibly one of the largest quantum systems in the known universe. Studying how quantum effects operate on such enormous scales provides insights into fundamental physics that could influence our understanding of quantum mechanics itself. The connection between Jupiter's interior and the broader cosmos becomes even more apparent when we consider how the quantum processes operating within the metallic hydrogen ocean might influence the planet's interactions with its environment. The quantum correlations within the ocean could affect how Jupiter responds to external perturbations, from the gravitational influences of its moons to the impact of charged particles from the solar wind. These quantum effects might also influence the long-term evolution of Jupiter's interior structure. As the planet continues to cool and contract over billions of years, the quantum properties of the metallic hydrogen ocean will change in ways that could fundamentally alter the circulation patterns and magnetic field generation within the planet. Understanding these quantum evolutionary processes is crucial for predicting how Jupiter will change over cosmic timescales. The exploration of Jupiter's metallic hydrogen ocean through the Juno mission continues to reveal new aspects of this quantum fluid environment. Each orbit provides additional data about the magnetic field structure, gravitational anomalies, and circulation patterns that help constrain our theoretical models of how quantum processes operate under extreme conditions. The measurements of Jupiter's magnetic field have revealed temporal variations that might reflect changes in the quantum state of the metallic hydrogen ocean. These variations occur on timescales of months to years, much faster than the circulation patterns we observe in the fluid dynamics of the ocean. This suggests that quantum effects might provide additional mechanisms for change and evolution within Jupiter's interior that operate independently of classical fluid dynamics. As we float here in our imagination within this vast quantum ocean, surrounded by metallic hydrogen that exhibits properties beyond our everyday experience, we can appreciate the profound mystery that still surrounds these exotic environments. The quantum effects we've been exploring represent just the beginning of our understanding of how matter behaves under the extreme conditions found within giant planets. The metallic hydrogen that surrounds us carries within its quantum structure a record of Jupiter's formation and evolution over billions of years. The quantum correlations that extend throughout the ocean preserve information about conditions that existed during the early solar system, when Jupiter was still accreting material and establishing its internal structure. By studying these quantum signatures, we might be able to reconstruct the history of processes that occurred during the first few million years of our solar system's existence. The circulation currents that move through this quantum ocean transport not just heat and materials, but quantum information itself. As quantum-correlated regions of metallic hydrogen are carried between different parts of the ocean by convection currents, they create pathways for quantum communication that span thousands of kilometers. This quantum communication network operates continuously within Jupiter's interior, creating correlations and influences that connect every part of the planet to every other part through quantum mechanical processes. The study of Jupiter's metallic hydrogen ocean is revolutionizing our understanding of how quantum effects can operate on macroscopic scales. The traditional view that quantum mechanics only applies to microscopic systems is being challenged by the realization that under extreme conditions, quantum effects can dominate the behavior of systems as large as planetary interiors. These discoveries have implications that extend throughout the field of physics, from our understanding of superconductivity and superfluidity to the development of quantum technologies here on Earth. The natural quantum laboratory that exists within Jupiter's interior provides insights into quantum phenomena that cannot be studied in any terrestrial laboratory, no matter how sophisticated. As we continue our ascent through this remarkable quantum ocean, approaching the boundary where metallic hydrogen transitions back to liquid hydrogen thousands of kilometers above us, we carry with us an appreciation for the incredible complexity and beauty of the quantum world that exists within our own solar system. The phenomena we've explored challenge our understanding of the relationship between quantum mechanics and classical physics, revealing that the universe operates according to principles that are far more subtle and interconnected than our everyday experience might suggest. The quantum effects within Jupiter's metallic hydrogen ocean remind us that the cosmos contains realms of experience that stretch far beyond our terrestrial perspective, where the familiar rules of chemistry and physics give way to more fundamental quantum principles that govern the behavior of matter and energy under extreme conditions. These exotic environments serve as natural laboratories where the universe experiments with the fundamental properties of quantum systems on scales that dwarf anything we can create or study directly. Tonight, as you rest beneath Earth's familiar sky, remember that you share this solar system with quantum oceans that stretch across thousands of kilometers, where matter exists in states that bridge the gap between classical and quantum physics, and where the very structure of reality operates according to principles that continue to challenge and inspire our understanding of how the universe works at its deepest levels. the exploration of Jupiter's quantum metallic hydrogen ocean brings us face to face with one of the most profound realizations about our solar system. We are not merely exploring a large planet with unusual properties. We are witnessing the emergence of complexity from simplicity, order from chaos, beauty from the fundamental forces that govern all matter in the universe. As we begin our ascent from the metallic hydrogen ocean toward the liquid hydrogen regions above, we encounter boundary zones that challenge our understanding of how phase transitions occur under extreme conditions. The transition from metallic to liquid hydrogen doesn't happen suddenly, like ice melting into water. Instead, it unfolds gradually across thousands of kilometers, creating intermediate states of matter that exist nowhere else in our solar system. In these boundary regions, approximately 15,000 kilometers below Jupiter's cloud tops, the quantum properties we've been exploring begin to fade as the extreme pressures that create metallic hydrogen gradually give way to the more familiar behavior of compressed liquid. But this transition creates opportunities for phenomena that are even more exotic than the pure quantum states we've been discussing. The materials in these transition zones exist in what physicists call a critical state, poised precisely between metallic and non-metallic behavior. Small changes in pressure or temperature can tip the balance one way or another, creating regions where the same material exhibits different properties depending on local conditions. It's as if we're exploring a landscape where the fundamental nature of matter itself changes with the terrain. The convection currents that transport materials through these critical regions create mixing processes of incredible complexity. As quantum-correlated metallic hydrogen rises into regions where the pressures are insufficient to maintain metallic behavior, the quantum correlations don't simply disappear. Instead, they undergo a gradual decay process that can extend across hundreds of kilometers, creating zones where quantum and classical behaviors coexist in delicate balance. These mixed quantum classical regions might hold the key to understanding some of Jupiter's most puzzling properties. The planet's magnetic field shows variations and anomalies that don't match our predictions based on simple models of metallic hydrogen convection. But if quantum effects persist into regions where we wouldn't normally expect them, these hybrid zones could create additional sources of electromagnetic activity that contribute to Jupiter's complex magnetic field structure. The chemical implications of these transition zones extend throughout Jupiter's interior and into the observable atmosphere above. Trace compounds that are dissolved in the metallic hydrogen ocean undergo their own phase transitions as they encounter changing pressures. Some materials that exist in exotic quantum states within the metallic region might crystallize into more familiar forms as they rise into the liquid hydrogen zones above. But these aren't ordinary crystallization processes. The extreme pressures and temperatures involved create opportunities for crystal structures that would be impossible under normal conditions. These high-pressure crystals might possess properties like piezoelectricity, generating electrical currents when subjected to mechanical stress, or ferromagnetism, creating their own magnetic fields that interact with Jupiter's primary field. The formation and dissolution of these exotic crystals as materials circulate through the transition zones creates a kind of geological cycle within Jupiter's interior. Crystals that form in the high-pressure regions might be carried upward by convection currents until they reach zones where the pressure is insufficient to maintain their structure. As they dissolve, they release the chemical energy that was stored during their formation, contributing to the heat transport that drives Jupiter's internal circulation. This crystalline cycle operates on timescales that span millions of years, creating a slow rhythm of formation and dissolution that has persisted throughout Jupiter's history. The crystals that exist within Jupiter's interior today might be the descendants of structures that first formed during the planet's early evolution, modified and transformed by billions of years of circulation through different pressure and temperature environments. The magnetic field interactions in these transition zones create phenomena that bridge the gap between the quantum effects we've explored and the more classical magnetohydrodynamics that operate in the liquid hydrogen regions above. As quantum correlated materials from the metallic ocean encounter changing magnetic field conditions, they can create persistent current loops that maintain their own magnetic fields even after the quantum correlations have decayed. These persistent currents act like magnetic memory elements within Jupiter's interior, preserving information about past configurations of the magnetic field and circulation patterns. Over long periods, the accumulation of these magnetic memories could influence the overall evolution of Jupiter's magnetic field, creating feedback loops between past and present conditions that help maintain the complex field structure we observe today. The Juno spacecraft has detected magnetic anomalies that might represent the signatures of these persistent current systems. Small-scale variations in the magnetic field, strength and direction could reflect the presence of current loops that formed during earlier epochs of Jupiter's evolution and continue to influence magnetic field generation today. These magnetic fossils provide windows into Jupiter's past that complement the chemical and thermal signatures we've been exploring. The temperature gradients across the transition zones create thermal environments that span an enormous range, from the scorching conditions near the metallic ocean boundary to the relatively cooler regions where liquid hydrogen begins to dominate. This thermal diversity creates opportunities for chemical reactions that couldn't occur in more uniform environments, where reactants and products exist under vastly different conditions within the same general region of Jupiter's interior. The circulation patterns that transport materials through these thermal gradients act like conveyor belts for chemical processing, carrying reactants from hot regions where certain reactions are favored to cooler zones where different processes dominate. The result is a kind of chemical factory that operates continuously on planetary scales, producing compounds and materials that reflect the unique conditions found within giant planet interiors. Some of these chemically processed materials eventually make their way to Jupiter's upper atmosphere, where they contribute to the complex chemistry that creates the planet's distinctive appearance. The subtle color variations we observe in Jupiter's cloud bands might reflect trace compounds that were processed in the transition zones thousands of kilometers below, carried upward by convection currents and transformed multiple times during their long journey to the surface. The isotopic signatures of these transported materials carry information about the conditions under which they were processed, providing clues about temperatures, pressures, and chemical environments that exist deep within Jupiter's interior. By studying the isotopic composition of gases in Jupiter's atmosphere, scientists can infer properties of regions that no spacecraft will ever directly sample, using the atmosphere as a window into the hidden processes operating in the planet's depths. The ongoing research into these transition zone processes is revealing connections between Jupiter's interior structure and the planet's role in the broader architecture of our solar system. The materials that Jupiter processes within its interior don't remain permanently trapped within the planet. Some eventually escape through atmospheric loss processes or through interactions with Jupiter's magnetosphere, becoming part of the interplanetary environment. These escaping materials carry with them chemical signatures that preserve information about the extreme conditions within Jupiter's interior. When these materials interact with other bodies in the solar system, they create chemical deposits that serve as geological records of Jupiter's internal evolution. The surfaces of Jupiter's moons show evidence of chemical alteration by materials that originated deep within the planet, creating archives of information about processes that operate in regions we can never directly observe. The connection between Jupiter's interior processes and its moon system extends beyond simple chemical deposition. The tidal forces that Jupiter exerts on its moons are influenced by the planet's internal structure, particularly the distribution of mass within the interior. Changes in Jupiter's internal circulation patterns or the formation and dissolution of dense regions within the transition zones could subtly alter these tidal forces, influencing the geological evolution of the moon system over long periods. Europa's subsurface ocean, which might harbor conditions suitable for life, exists within this complex web of interactions between Jupiter's interior and its satellite system. The chemical diversity created by processes operating within Jupiter's transition zones might provide raw materials for complex chemistry within Europa's hidden sea, creating opportunities for prebiotic processes or even life itself in an environment that seems far removed from the extreme conditions of Jupiter's interior. The study of Jupiter's transition zones also provides insights into the formation and evolution of giant planets throughout the galaxy. As we discover more exoplanets orbiting other stars, many of them turn out to be gas giants with masses and compositions similar to Jupiter. The lessons we learn about how materials behave and evolve within Jupiter's interior provide a framework for understanding how these distant worlds might be organized internally. The extreme conditions we've been exploring within Jupiter's transition zones might be common features of giant planet interiors throughout the universe. The quantum effects, exotic phase transitions, and complex chemical processing that we observe within Jupiter could be universal characteristics of worlds that form through the accretion of hydrogen and helium around solid cores. This makes Jupiter a crucial laboratory for understanding planetary processes that operate throughout the cosmos. The ongoing evolution of Jupiter's transition zones continues today, billions of years after the planet's formation, driven by the slow cooling and contraction that will persist for billions of years into the future. As Jupiter gradually loses heat to space, the boundaries between different phases of matter within its interior will shift and evolve, creating new transition zones while modifying existing ones. Computer simulations suggest that this thermal evolution will proceed so slowly that the basic structure of Jupiter's interior will remain essentially unchanged over the entire future history of our solar system. The Sun will exhaust its nuclear fuel and begin its evolution toward a white dwarf star long before Jupiter's interior structure undergoes any fundamental changes. This stability ensures that the processes we've been exploring will continue operating according to the same basic principles for cosmic ages to come. As we continue our ascent through these remarkable transition zones, approaching the vast liquid hydrogen regions that extend thousands of kilometers above us, we can appreciate the incredible journey we've undertaken through one of the most complex and dynamic environments in our solar system. The quantum effects, exotic phase transitions, and chemical processing we've explored represent just a fraction of the phenomena that operate within Jupiter's hidden depths. As our extraordinary journey through Jupiter's hidden depths draws to a close, we find ourselves forever changed by what we've witnessed in these alien realms. From the diamond rain falling through metallic hydrogen seas to the quantum oceans that stretch beyond imagination, we've explored a world that challenges everything we thought we knew about the nature of matter and energy in our universe. Tonight, as you rest beneath our familiar Earth sky, remember that somewhere out there in the cosmic darkness, Jupiter continues its ancient dance through space, its interior churning with processes more magnificent and mysterious than any earthly wonder. Sweet dreams, fellow traveler, and thank you for joining me on this incredible voyage through the heart of our solar system's greatest giant. I hope you had an amazing time with me here at Boring Science. I will see you tomorrow as always. Until then, stay curious, keep wondering. This is Boring Science signing off. Cheers.